talked about this, and you've kind of seen how stirring or heating can affect the rate of dissolution. There are just a few other ideas to hit on this, and one of them is this, solvent-solute interactions. So, does water dissolve everything? No. It doesn't dissolve grease. If you've ever tried to get grease off your hands with pure water, you cannot rinse off grease. You may have had an experience recently where you used a fat in a chem lab and got it all over your glassware, and you can't just give that a rinse. It takes soap. It takes something that's going to lift that off. The relationship is really polar versus nonpolar. So water is a polar substance, remember? It's a polar molecule because it has a region of what? Partial charge. So polar molecules have regions of charge on them. Well, things that are polar really dissolve other things that are polar very nicely. Nonpolar substances, and guess what? Oil is a nonpolar substance. Nonpolar substances are not well dissolved by polar solvents. Like dissolves like. So, if you've got grease, you're going to use water to dissolve it or something nonpolar like gasoline. You're going to use gasoline. If you have ever walked into an auto shop, if you know anybody who, I have a cousin who's a mechanic, and I worry about him because the world of cars and motors and engines is heavily grease laden, and that means a lot of solvents, and they're really fairly toxic, nasty solvents. Like, you and I both said, yeah, how do you get the grease out of wheel bearings? Gasoline! My dad would take a milk jug and he'd cut it off and we'd fill it with gasoline. And now he did make me wear gloves. He would make me wear little latex gloves, and I had the small hands when I was a kid, so I got to swish it around in the gas. Is that a good idea? No, not at all. You don't want exposure to a lot of petrochemicals like that. In most auto shops, there is a big bin somewhere in the back that's called the parts washer, and it's got really nasty, dirty-looking fluid in it. It smells, the smell of it will pretty much get you high from 10 feet away, unless they've really improved the solvents they're using. It kills brain cells, and it is fantastic, petro-nasty, bad stuff kind of solvents, but boy does it strip grease off of parts. It's fabulous. Those are nonpolar solvents and nonpolar substances. So when you have that parts washer, okay, so in this parts washer, on one side, you've got relatively clean solvent. It's relatively clear. It's probably an unsaturated solution, okay? You can continue to clean parts in that. On this side, and you can just sort of see a peek of it, do you see a difference in the solvent? You can't see through it. It's very dark. That has a lot of grease dissolved in it. Now, in that case, what's the solute? What's the solute on this side? The grease. Yeah. Will there come a point where the solvent in your parts washer needs to be changed? Why?
Because it can't take any more grease on.
Because it is what? It's saturated. At the point where the fluid in the parts washer is saturated, you have to swap out the fluid. It cannot absorb any more of the solute. So you've got to change the fluid. Okay. We do talk about this a little bit differently when we have two liquids that we're putting together. We think about more of them mixing rather than them dissolving. But if they mix evenly and they mix nicely, they make a solution together. And the word we use for two liquids that will dissolve in one another, that will mix evenly, is miscible. So, can of pop, well, no, that's a terrible example. Okay. Beer is the only good example I got. Ethanol is the alcohol which people consume. Alcohol and water are miscible. Pure alcohol will kill you, and it draws water anyway. All of the ethanol that humans are consuming is a solution of water and ethanol. They're miscible. There are some liquids that don't mix. Oil and water. Salad dressing. Who here has made? Oh, vinegar and water. Duh, vinegar and water are totally miscible. It's a aqueous solution of acetic acid mixed with some more water. Totally miscible. When you make salad dressing, you put the water in, you put the vinegar in. Those mix up just fine. They're miscible. You put the oil in, now you have a layer floating on the top because those are immiscible. That's not what we can say there. So, pressure. We've been talking about pressure with gases quite a bit. Pressure doesn't really affect two liquids. Liquids are not all that compressible. You know that. Pressure does not affect solids. Temperature has a huge effect on solids. Try alloying silver and gold together at room temperature. Not going to happen. You need to get them into a liquid form. However, when we're talking about dissolving a gas into a liquid, pressure has a huge effect. There's a huge relationship between pressure and the solubility of gases into a liquid. So, it is directly proportional to the partial pressure of that gas on the surface of the liquid. Greater pressure, more gas can be dissolved in the liquid. Think about a 2-liter bottle of pop. What do you hear when you turn the cap? Everybody do it. Psst. That's pressure escaping. That carbon dioxide is forced into the liquid under high pressure. If you leave the pressure off, you allow the contents of the 2-liter. So basically you leave it open and you leave it, even in the fridge, you're allowing the contents of the bottle to adjust to atmospheric. What starts to happen to the carbon dioxide that's in the pop? Comes out of solution. Because at atmospheric pressure, once you break that seal, once you open the pop, it's no longer, the contents are no longer pressurized. And so it's now adjusted to atmospheric pressure. And at atmospheric pressure, carbon dioxide is not all that soluble in water. At high pressure, it's pretty darn soluble, and we've got a whole industry to prove it. So the more pressure you have, the more gas you can get dissolved in a liquid. Now, there is a physical limit to what a 2-liter pop bottle can hold. I can tell you this from experience because I blew one up making homemade ginger beer. Just yeast and ginger root and water and sugar, and it's just, homemade ginger ale, root beer stuff. And it turns out there is an upper physical limit to the plastic on a 2-liter pop bottle. Whoops. It's not just a game anymore. So this is how much solute is in a solution. Okay? There are a couple different ways to measure it. If you think about concentration in these terms, if you make Kool-Aid and you put a 1/4 cup of sugar in your 2 quarts of Kool-Aid, that's fairly dilute. If you take Kool-Aid and you put 2 cups of sugar in your 2 quarts of water, that's pretty concentrated. So you started to get at that with your solubility tables and looking at how many grams of solute per grams of water. The more grams of solute per grams of water, the more concentrated it is. But we have to have a better way than that to measure it. So the most common way that we measure concentration of solutions is what's called molarity. Okay? And molarity is the number of moles of solute per liter of solution. Pretty easy. Molarity, this is where it gets weird and complicated. Notice that molarity is abbreviated with a capital M. There's also molality, which is a lowercase italicized m, because we couldn't think of another letter. And then there are moles, M-O-L, and then there are meters, lowercase m. So it's really important that you know that that is molarity. There are 2 ways to measure concentration. This is the most common and the most useful one. A 1 molar solution is 1 mole of stuff in 1 liter of solution. Couldn't be easier. If you want to make a 1 molar solution, for instance, of sodium hydroxide, molar mass of 40 grams. You put the 40 grams into a flask, and then you add water up to the 1 liter mark. You don't add a liter of water, because you'll actually end up that way with more than a liter of solution, and that's a less concentrated solution. So what we have to do this are these things that are called volumetric flasks. You know, we talked about the fact that these flasks are not terribly precise in terms of measuring volume. That 500 milliliters line on there, it says plus or minus 5%. Not real exact. If we need to have a very exact volume of liquid, we need to use what's called a volumetric flask. And this one says 500 milliliters plus or minus 0.4%. So a much higher level of precision. So we would put our sodium hydroxide into here. Then we would fill it up to the 500 milliliter line. And we'd probably set it on a stir plate and agitate to get it all dissolved. And that's a 1 molar solution. Pretty easy, right? So let's look at the formula, how this is expressed formulaically. Molarity is the amount of solute over the volume of solution. And you can solve for anything in there. So let's practice. And I will assign the practice problems on 414, but first I want to do something together. So we have our sodium bicarbonate up here. And sodium bicarbonate, you might remember, or you might not, is HCO3. That's sodium bicarbonate. There's the sodium ion, there's the bicarbonate ion, or hydrogen carbonate ion. That's sodium bicarb, the stuff that comes in the box. You might keep it in your fridge. You might put it in the kitty litter. You might wash your hair with it. You might brush your teeth with it. I don't know what you do with it. Anyway, that's it. So if I wanted to make a 1 molar solution of sodium bicarbonate, what's my first step? Well, let's look at this formula. So molarity is equal to the amount of solute in moles over the volume of solution. So if I want to make a 1 molar solution of sodium bicarbonate, I need to know moles over liters. And 1 molar would be 1 mole over 1 liter of solution. Sadly, I do not have a balance in here that balances in moles. So what's my first step? I got to figure out how many grams of sodium bicarbonate I need. So I know that I'm going to have 1 liter of solution. I also know that I want 1 mole of sodium bicarbonate. So NaHCO, so 16 times 3, 12.01, 1.01, 22.99. What do we get for a raw value on that? I actually did it on a piece of scrap paper over here. So I get 84.01 grams of sodium bicarbonate. Don't know why I can't draw an N. Okay, great. Now what? Yeah, we could do that. We could do that. You're absolutely right. So, we know that we want 1 mole of sodium bicarbonate. We know that 84.01, whoops, just screwed that up. 84.01 grams of sodium bicarbonate is equal to 1 mole of sodium bicarbonate. So I know that I'm going to use 84.01 grams of sodium bicarbonate. And I'm going to basically put that into a container. Oops. There's my little pile of sodium bicarbonate. And I'm going to fill it up to the line in a volumetric flask that says 1 liter. And I'm done. So here's the other question. What if I want to make 500 milliliters of 1 molar sodium bicarbonate? Because sometimes you don't want to make a whole liter of solution. That's a lot of solution. Maybe I only have a 500 milliliter volumetric flask. Maybe I don't have a 1 liter volumetric flask. You lost a lot of glassware on the move. Well, if I want to make 500 milliliters of 1 molar, still in the face? Yes. 1 molar sodium bicarbonate solution. How much sodium bicarbonate do I need? Okay, what's my first step? Well, I look at this. Molarity equals number of moles per liters of solution. Well, I still want 1 molar. I'm really solving here for the number of moles that I need. So molarity times the volume of the solution equals the number of moles. And I want 1 molar solution. I want 0.5 liters. How many moles do I want? Well, I want a half a mole. I know, you could have all done this in your head. But we're going to make it more complicated, trust me. So I want 0.5 moles of sodium bicarbonate. Well, that's pretty easy because all I have to do is a factor label. Whoops. Starting with 0.5 moles sodium bicarbonate. We already established that 1 mole of sodium bicarbonate is 84.01 grams of sodium bicarbonate. So what do we get? 42-ish? 42.005. Oops. So we get 42.005 grams of sodium bicarbonate. That's what we need to make a half liter of 1 molar sodium bicarbonate solution. Does that seem straightforward? Okay. Let's do one more complicated one, and then I'm going to cut you loose on the practice problems. So what if I want to make 250 milliliters of, what's a common one? Let's do 0.1 molar sodium chloride solution, a saline solution. You know what, we'll stick with the sodium bicarbonate. We've got the mass figured out and everything. Okay. Okay, so to make 250 milliliters of a 0.1 molar sodium bicarbonate solution, what mass of solute is needed? Where do we start? Well, we need to figure out how many moles of sodium bicarbonate we need before we can figure out how many grams. So we have to actually start with that formula for molarity that relates molarity, liters of solution, and number of moles. So molarity equals number of moles over liters of solution. We need to solve for moles. So the molarity times the volume in liters equals the number of moles that are required. We want 0.1 molar solution, and we want 0.250, or nope, just 0.25 liters of solution. So how many? So we need 0.025 moles. Not a lot. Now let's figure out how many grams that is. So now that we know how many grams we need, we can do a factor label. 0.250 moles of sodium sodium bicarbonate. Why do I keep saying sodium hydroxide? Where we know that 1 mole of sodium hydroxide. Oh, it is. Thank you. I screwed that up. There. Is that better? Okay. 84.01 grams of sodium hydroxide. Whoops, well. So how many grams of sodium hydroxide do we need? Raw number for this? Okay, 2.10025 grams. It's not a lot. This is a really dilute solution. Does this make sense? Okay. So what I'm going to have you do on page 441, I believe it was, in here, there are some practice problems. Okay, chapter review. This is chapter 13, numbers 16 and 17, and I'll cut you loose to work on that. And I'll float around.